We next want to implement closures in our model. As we have seen, there are three kinds of closures. Triadic closure, we both have a common friend, we become friends. Foci closure, we both are going to the same gym, so we become friends. Membership closure, I am your friend, you go to gym, so I start going to gym. So how do we implement these closures in our model is now the question. So how have we implemented these closures before? So we have used a formula, if you remember. So what we have done is, if there are two people A and B, and these people have, let's say, some k number of common friends, then assume that each of these common friends contributes to a probability P. So one common friend contributes to a probability of P that these two people will become friends. Assume that it's 0.4. So one person says that with 40% probability these two people A and B will become friends. And then we looked at this formula that the probability that these two people will become friends in the next iteration is 1 minus p to the power k. So we will be using the same formula for implementing all three kinds of closures. Now how do we implement it? First, we look at every two possible combination of nodes. So when we pick two nodes from this network, we will pick every possible pair of two nodes. So when we pick these two nodes from the network, what can be their types? So both of these can be the person nodes, person A, person B, or one can be a person node and another can be a foci node. So person and foci node, or vice versa, foci node and person node. So mainly one person node and one foci node, and in the last case both of these can be the foci node. How do closures happen in all of these three cases? So in the first case, when there are two people node, so if we look at the common neighbors of these two nodes, so we know that in our model the common neighbors can be a person as well as a foci. So we use the same formula for both of these things. So we capture both the triadic closure and the foci closure using the same formula. So we assume that whether it's a person which is their common friend or it's a foci where both of these are going, contributes to a probability P of them becoming friends. So as I told you that this is a very, we are trying to keep things very simple here. So once we write the complete coding, we can actually change both of these probabilities. We can assume that or we can code it that if there is a person node, it has a higher probability of making them friends, and if it is a foci node, it has a less probability of making them friends. But for now we keep both of these the same. So whether it's a common friend or a common foci, it contributes to a probability P of both of these becoming friends, and then again we use the same formula. So that formula helps us in achieving both things here, triadic closure and foci closure. Let's now look at the second case. So here is a person and then here is a social foci. Now we look at their common neighbors. Now if you look at their common neighbors, do you observe that their common neighbors can only be persons? Their common neighbors cannot be foci. Why? Because there are no edges between the foci nodes. So two foci nodes are never connected to each other. The edges are only between person to person and person to foci. So we have a person and we have a foci here, and all their common neighbors are different persons. So this means that this person here can have k of his friends going to this social foci, and again we assume that each of these common friends contributes to a probability of P for this person also to go to the social foci, and again we use the same formula. So you see how we just use one formula for implementing all these three kinds of closures. Once we code it, we can actually change the things here and make it more advanced. Next, we want to implement closure property in this graph. So for meantime, we comment the homophily so that we can clearly see what is happening in closure, and we have here closure G. So as we have discussed, there are three kinds of closures which we have to implement. We come here, define,
closure G. And what we have to do for closure is, we know that in one iteration everybody is going to look at their common friends to any two people, or any two people, they are going to look at all their common friends and they are going to decide whether in the next iteration they are going to connect to each other or not. So what we do here is take an array, let's say array 1, and this array will have 3 values. So how will this array look like? This array will be composed of subarrays, and each subarray will be having 3 values. The first value is the first node, second value is the second node, and third value is the probability of connection. So when we are going in an iteration of closure G, we do not keep adding edges side by side like we did for homophily, because if you add an edge between, you looked at 1 and 2 and you added an edge between them, it can have complications for the addition of the coming up edges. So the addition of every edge should be independent of what has been added before. So to maintain that independence, we have here this array, array 1, and so these are the kinds of values this array 1 will hold. So here it can be 2, 5 and then 0.7 and so on. So how do we go about doing this? So initially we have this array 1 which is empty, and then now after looking at all the nodes and their common neighbors, we have to decide whether we have to add an edge between them or not. As we have seen that for any kind of closure to happen, the only condition required is whatever nodes we are picking, both of those nodes should not be the foci nodes. Otherwise, if both of them are the people nodes, it results in a simple closure. And otherwise, the other two cases result in a membership closure and a foci closure. The only condition is both of the nodes should not be foci nodes. What do we do is, for U in G dot nodes, and then for V in G dot nodes. Now both of these nodes should not be the foci nodes, at least one of these should be the person node. So if first of all U is not equals to V, and either G dot node of U, G dot node U type equals to person, or G dot node V type equals to person. So one of these should be person. In that case, we have to implement our closure. We already know what was our formula for closure, and we are using that same formula for all three kinds of closure. So here we find out the value of a probability P, which is nothing but our formula. So our formula was 1 minus P to the power of K. So for having 1 minus P to the power K, we have this function math dot power. So we have to add this package math at the top, which will do. So 1 minus math dot power and power 1 minus P to the power of K. But now what is K here? K is the number of common neighbors. So we need the number of common neighbors between U and V. So we have here K equals to find common neighbors. So let's have simple function name CMN common neighbors between U and V in the graph G. So now we need to define this function here. Define CMN common neighbors of U, V, G. And how do we find its value is, first of all we need the neighbors of U. So neighbors of U equals to G dot neighbors of U, and then neighbors of V equals to G dot neighbors of V. And we want the common one. So for having common one, we need a set intersection. So let's make both of these values as sets. So nu is a set having the neighbors of u, and nv is a set having the neighbors of v, and what we have to return is the length of the set, which set nu and nv, which only looks at the common elements of u and v. So we return length of nu and nv. Okay, so we have this probability here, math.power 1 minus p to the power of k. Now we have to feed these values inside our array, which has to have three parts, u, v and the probability of connection. So we need a sub array here. Let's name it temp. So the first value which we are going to append to temp is u, and the second value which we are going to append to temp is v, and then the third value which we append to temp is p. So temp has these three values, and at the end we append temp in array 1. Array 1 dot append temp. So we have made here this array 1 for all possible pairs of nodes. Let's quickly look at how this array 1 looks like. So let's print array 1 and see how it looks like. We forgot to import the package math. We go up and here we import math, and at the end, okay, this has become a big code. So at the end, for the time being, we comment our visualize functions as well. And now let's look at the array. Okay, there is some problem. Okay, so this p here, the p in the formula, this p here was supposed to be a constant. What was that constant value of probability? That is the probability each of your common neighbor contributes to you forming a connection. Let's come back. When we come here to closer, p equals to, this probability is supposed to be some value here. So let's say each of my neighbor contributes a 0.01 probability of connection. Let's rather say 0.1 probability of connection. Then the more common neighbors we have, more our probability of connection becomes. Let's go back, execute it. So now you can see here your array, and as we can see that as of now most of the values are here 0, and there is a reason for it to be 0, because there are very less common neighbors here. So you can see here in some cases we have here this value here 0.09998. So since it is the very beginning of our code, so initially we had seen that the common neighbors only exist between. So there is no homophily as of now. We have commented the function homophily. The common neighbors will exist only when two people are the part of same social foci. So you can see here, if we look at the nodes here, 187 and then 174, 156. So these are mostly the people node which are connected to the same social foci, and this is the probability of these two nodes getting connected with each other. So if we apply a closure here, it's mostly, since there is no edge between two people, it's mostly going to be happening a foci closure only. Okay, so we here was this array 1. Now we have to make edges in accordance with this array 1. So that is very simple. So we go for each in array 1. So for every entry in array 1, what do we do? Our first value, first node is each 0, and then our second node is each 1, and then our probability of connection is each 2. As we have done before, we choose a random real number from 0 to 1, r equals to random dot uniform 0 to 1, and if r is less than p, we add an edge. G dot add edge between u and v. So this is one iteration of our function closure. Let's execute and see it. So here we'll be visualizing our graph as well. So this is how our initial graph looks like. Let's see what's going on here. So actually there are no intersections here. It has just okay. So you can see here every node is actually the part of exactly one social foci here. You can zoom this graph and see. And now this is what happens after closure. So let us see what has happened after closure. Let's look at this. So you can see that there are more and more edges which have been added between people. So 18 has now become connected to 28, 28 has become connected to 24 because they were all the part of the same social foci gym. So you see how here the edges between people have been added. So as we can see here that probability of connection seems to be very high. We do not want this high probability of connection. So for that what we can actually do is we go back and we reduce this probability here. So let's say one common neighbor contributes 0.01 probability of connection. Let's now look at. So this is our initial graph and let's see what happens here now. Let's again pick one here. Let's say we pick this karate club, and then you can now here see that the probability of connection has reduced. So this karate club leads to the formation of some number of edges between two people. Okay, we might want to see other kinds of closures as well. So till now here only two people were getting connected to each other because of having a common social foci. So for that we would like to do homophily first so that we have some edges between the people as well, and then we visualize and then we apply closure. So for looking at, so let's for the meantime reduce this value. And actually differentiating between the triadic closure and foci closure is a little bit difficult because there the edge added is between two people only. We would like to look at the membership closure where one person becomes a part of social foci because his friend is a part of social foci. So let's try to look at that. I put this code in a loop. So while one closure happens, and it keeps visualizing it again and again. So this is homophily. So this is the graph. Now you can see here, right, this node 35, it is going to the karate club as well as it is going to the gym. So this node 35, it has two social foci here in which it is participating, but according to our code initially one node was assigned to exactly one social foci. So most probably 35th node was initially a part of karate club only. As we see, then it has identified that one of its friends 19, 20 or somebody was going to gym, and hence 35 also decides to go and be a member of gym. So we can actually see a membership closure also happening here. You can write this code, play around with it and look and verify it further. And it will keep happening till I do not stop it. So let's just okay, so let's just stop it here. Control Z. I'll stop this code here. Okay. So till now what we have done is we have made a graph having 100 nodes with different BMIs where every node is part of exactly one social foci. Then we implemented homophily here, and then we implemented closures here, and we implemented all three kinds of closures: triadic closure, foci closure and membership closure, and we have also seen them happening on this graph.